All right, next up, catalysis. Okay, let's take a look at this reaction. So we have an alkene trying to add hydrogen gas onto it, adding hydrogen onto here on this two alkene, you can get an alkane. In this case, you get butane. But this reaction, it never happened. I mean, it happened, but this is so slow that we just assume there's nothing happened. Right? Why is this reaction proceeds so slow? Because the activation energy is way too high. This reaction will never happen. It'll probably take years just to happen. Right? Now, if we want to make this reaction happen, what can we do with the activation energy? Some of you probably think, oh, can we lower the activation energy? Yeah, that's the thing that we could do. Okay. All right. Let's say I have an analogy right here. If you're standing in this town, you want to go to the treasure. What can you do? Well, to be able to go from town to the treasure, you have to walk up the hill, right? So if you want to go to the treasure faster, there are two ways that you can do. Destroy the mountain, cut the mountain off if you could, right? Or go to a different path, make a tunnel or whatever that have you don't have to go up high, right? So you will get to the treasure faster. Same thing right here. So we this case in this situation we call catalysis, right? So a catalysis. So when we add a catalyst. So in this case, we use nickel, palladium, platinum. This guy will help adding hydrogen onto the alkene to make an alkane, right? And if you look right here, so this reaction doesn't go to the same route anymore, go to a different route, and this new route have much lower activation energy. I use kind of like squiggly line right here. And the reason is there are multiple steps in here, not just one step reaction like we will see. Once you add a catalyst, it goes to a completely different mechanism. They might have 3 or 4 steps in there, but all of them have much lower activation energy than the original route. Okay? All right, I'll give you some example right here. So let's killing bacteria. Well, not bacteria, so bacteria is not that cute. Okay, look like a evil bacteria. Okay, so let's say bacteria try to kill us. All right, so we try to so our human race try to fight back by making an antibacterial agent or medicine. Okay, we call antibiotic, right? And but killing bacteria is not that simple because the bacteria have a layer outside a cell membrane called cell wall, which usually found in plant, in algae, in fungi, or bacteria. Okay, maybe something more. So anyway, so that's a cell wall. Cell wall is made of peptidoglycan, looks like this. Okay, it's 2 sugar units connect to each other, right? So, excuse me. And so peptidoglycan or cell wall is usually a target for killing bacteria because cell wall gives bacteria a wall, maintain the structure and activity for the bacteria, which means that if we can destroy the wall, this cell wall, the bacteria should be dead. Okay, so peptidoglycan is usually a target for the antibacterial agent or antibiotic, but destroying the cell wall or peptidoglycan is not simple. Let's take a look right here. So water attack to break this bond, that's a mechanism. So we have a nucleophilic attack, loss of living group there. So we try to cut this bond. This process is called hydrolysis, which is the main mechanism of destroying the cell wall. But this reaction doesn't really happen because the activation energy is so high. Peptidoglycan is so stable, right? We can't really do anything with it. What do we do? Well, we use enzyme. We have lysozyme, which is an enzyme that catalyzes the hydrolysis of bacterial cell wall. So this is my lysozyme, a Pac-Man. Okay, so lysozyme which is an enzyme, gonna grab onto an area on the cell wall. Look like this. This is an enzyme. See that? And this enzyme will help make water become more nucleophilic or become better nucleophile, and water can attack that carbon right there and destroy the cell wall, cut that bond, destroy the cell wall. All right, and the reaction that happened with an enzyme, we call enzymatic reaction, goes totally different route from the original hydrolysis. Right, and all this could be many steps but all these steps have much lower activation energy than the original route. Okay, and that's how we kill bacteria. Ow, it hurts. Yay. Okay. All right, so that's the application of catalysis. Okay. All right, so this is I think. Oh, that's on. Give me 1 second. Here we go. All right, chapter 6, class activity number 2. I'm not sure you see it. Hold on. Let me pull it up. Here we go. Okay, so this one, this chapter is not difficult, but it just introduces you, make you more familiar with drawing the mechanism, which we're going to use from now on for the rest of the course, and go all the way to organic chemistry too, if you have to take it. All right. So all this class activity 2 will help you familiar with all those reaction for pattern in the reaction mechanism that you have seen. Right. We have question 1, question 2. Question 3 and 4, and I give you full answers. The key question 1, 2, 3, and question 4. Okay. All right, we're done with chapter 6. Let's move on to chapter 7.